Now let's begin the second session. So in the last session, we discussed that we can we can also have a scalar potential for the auxiliary field H, and now this H field and obeys the Poisson's equation, and because here on the right hand side there is a source term, the del dot m is similar to some charge, and now this charge, if this charge is 0, then we have a Laplace equation. So we can apply that all we have learned in the chapter 3 about the potentials to solve this scalar potential. So for example, here we want to calculate the if we want to calculate the magnetic field inside a uniformly magnetized sphere. So that's the exact same problem that we have just discussed earlier in the in the earlier session, that we simply map that to an electrostatic problem by mapping the D so earlier we mapped the P and M and also the E and H. So now we can even have more mathematical meanings to this mapping. So instead of directly using the mapping and rewrite the equation, we can directly solve the problem in terms of the mathematical tools here by recognizing the del dot m as a source term. So here's the boundary conditions. This W base is the same for what you have in this what you have in the V, the scalar potential for the electrostatic problem. So if you still remember, the V is always continuous in the static problem. So here the W, the another scalar potential, is also continuous everywhere across any boundaries. But this derivative, or this derivative along the normal direction is not continuous, and the difference or the discontinuity of the derivative of the scalar potential is related to this. If you remember the charge at this surface. Now this charge translates to del dot m, and on this edge, this delta m is m dot n hat. So if you remember, the delta dot m is the expression for the surface bound. For delta dot m is the if you remember, the term relates to the bound volume free bound volume charge, and the P dot n is related to the bound surface charge. So why it's written as the m dot n is because it follows the logic here. And so on the boundary, this boundary condition is simply rewritten as m dot n. I think you can also obtain this by enclosing a Gaussian Gaussian surface volume to near the surface of the edge. And now we can simply apply the truth here to this problem. So here for the uniformly magnetized sphere, one of the conditions is the first one. So the inside W and outside W is exactly equal to each other. So if you remember what we have done when we calculate the uniformly polarized materials, we also calculated the we also studied the same problem using the scalar potential V. So here we are simply doing the same thing, but in terms of the W now. So sorry. So here the first condition is simply being copied down, and the second condition is the discontinuity at the surface. So because this is a uniformly sphere, the n hat direction is along this r hat direction, and now because say that because this is uniform, we need to choose a direction of this uniform vector. So for uniform vector field, it must has an orientation, and we say that here we choose the orientation to be the z-axis. So m vector is along the z-axis now, and then the z dot r, z hat dot r hat is simply the angle between the r hat vector and the z-axis. So the z hat is here, and the r hat is here. So the angle is the theta, and the dot product of r hat and this hat is simply the cosine theta, and so then the boundary conditions are simply being listed here, and because this is azimuthal problem with azimuthal symmetry, and this is a spherical problem, so we have to be so we are able to use the what we have learned in this chapter 3 about the potentials. Now if we study the field completely inside this surface, so here we want the field inside this sphere, then the field can be described by the Laplace equation, because all this discontinuity is at the edge. And now if we study the field outside this surface, we can again use the Laplace equation to solve it. So in the end, what we have is a Laplace equation in a spherical coordinate and with azimuthal symmetry, and that's a set of problems that we studied in chapter 3 about the potentials. So then we immediately throw out the expression here. So we know that the solution must be a superposition of some solutions, and these solutions composed of two parts. One is a radial part that is proportional to one term is r to the L, and another term is r to the minus L minus 1. And another term, that's the angular term. So this is the spherical Bessel functions. And here this L is the angular momentum goes from 0 to infinity. So now this must be very familiar to you because you also seen this in the midterm, right? So if you remember in the inside, then this term diverge. So the BL must be exactly 0. And for the outside solution, this term diverge. So AL must be exactly 0. Now what you need to do is simply to apply this boundary conditions and to determine the rest of the BL coefficients. So now by observation, there must be a term that only involves P1 because there is a cosine theta term here. So I'll not go through the exact details, but what you need to do is simply to apply what you have for the inside. So and the outside solutions. And apply the boundary conditions that we have just used here and here. So now the first boundary condition is W inside equals to the W outside, and that gives us the AL must be related to BL by this R to the 2L plus 1. And then the derivative of this W, one is the inside, one is the outside derivative minus the inside derivative must be equal to the minus m cosine theta, which is the m dot n. And then this can simplify the boundary condition to be here. And now for L equals 1, this term is non-zero. And for everything else that's L not equals to 1, by simply looking at the boundary condition where there is only cosine theta term contributing, then we know that for every L not equal to 1, the coefficient must be exactly 0. So in the end, what we solve is the L must be m over 3 for L equal to 1. So that means that the W field here is m over 3 times r cosine theta. That is by collecting all the L equals 1 solutions. So I think that because the R is so this is the inside solution because here when R goes to infinity it diverge, and then we can simply but this is not the end of the story because the W is not a physical quantity, so it's only a mathematical scalar potential, and to get the physical quantity we need to calculate the gradient of this W function, and that gives back the H field. So from that we can get the H field, and then from the H field, if we combine this H field with this magnetization vector m, then Uh, then by plugging all these numbers, we get the final magnetic field to be 2 over 3 mu naught m along the z hat direction. And now if you compare the terms of here with what we just derived for this homework problem 6, this must be identical to each other. So this is a way of solving this magnetic problems using the what we have learned in this chapter 3, but without directly invoking the mapping between the electric field and the magnetic field. In principle, if you go back to this, if you map the system back to the electric field, we still need to go through the same mathematical steps to arrive at this final conclusion. So here, by directly recognizing this scalar potential W, we skipped all this mapping tricks and directly use this mathematical method to solve the problem here. So that's the subtle difference between what we have just used about this parallelism and the scalar potential W. Okay, so now let's go to the final topic in this magnetic fields in matter. So that is the ferromagnetism. So in our everyday life, we actually deal with the ferromagnetism rather often, comparing with the paramagnetic or diamagnetic materials, because the magnetic field produced by ferromagnetism is huge comparing to the magnetic response of diamagnetic or the paramagnetic materials. And there are 3 elements, the iron, the cobalt, and the nickel, that has very strong ferromagnetism even in room temperature. So in principle, there is a ferromagnetic to paramagnetic transition for these elements, and the transition point or the transition temperature is called the Curie point, and it's extremely high temperature for these 3 materials. So for iron, the temperature is 770 Celsius, and so in the room temperature is only about 20 Celsius, which is much smaller than the transition temperature. So for iron, it's typically a ferromagnetic material if it's not heated to very high temperatures. And the physical model to describe the ferromagnetism is complicated. And one of the simple models that captures the essential physics of the ferromagnetism is called the Ising model. So the Ising model has many different versions. So the classical, you can consider a Ising model in the classical physics, and I'm not sure if you can actually already study this statistical or thermal physics. If you have studied the statistical or thermal physics, you might have already learned about the Ising model, right? Okay. And then you can use quantum Monte Carlo to solve this. Sorry, you use simply. What? I'm not sure which. Maybe it's the 4th year. I don't remember exactly. But so if you haven't learned about this, you mean it's a selective course? Oh, do you mean that you learn the statistical physics in a selective course, or instead of a core course? Oh, okay, yeah, yeah, it could be a computational physics course, yeah. Um, so you might need to use Monte Carlo simulations to calculate the problem, and it might also work. It might also appear in quantum physics, maybe in graduate level. But so instead of doing classical spins, you can actually treat the spins quantum mechanically, and that's to solve the problem in low temperature, and this is called quantum Ising model, and you might learn about this later in the course, later in graduate level maybe. Um, so here, but the essential idea about this Ising model is that the spins in the materials are strongly interacting if they are close to each other. So here the spins, what I mean is that typically the materials are already magnetized. There are small magnetic dipole moment that's having random directions in the material, and the magnetic field can align this magnetic moment, right? But in this ferromagnetic materials, the spin and the spin, especially when they are close together, they can interact, and the interaction tends to align the two spins into the same direction. So say that you have a spin here, so it want to align with the spin left, spin to the right, spin to the up, and spin to the down. So eventually, for ferromagnetic material, they are not having random direction spins like what I shown here, but instead, the materials actually have a domain of spin, say up, and another domain, say maybe spin down, and some other domains spin to the right, and say that in this specific domains, they all share the same direction, but sorry, in the same regime, and okay, in the same domain, yeah, and this is called the the edge, or the that's near this two different domains is called the domain wall, and then this domain wall can on this domain wall, the spin doesn't have a specific direction, right? So because on the domain here it's pointing up, and on the domain here it's pointing to the right. So around the boundaries, the domains can either be pointing up or pointing to the right, and there can be some fluctuations, thermal fluctuations. But now, if you apply external magnetic field, say that I apply a field, magnetic field towards the direction of the right, then this domains the spins on top of this domain wall will prefer to align with the magnetic field, and this effectively increase the size of the domain of the spin to the right. So eventually, as you increase and increasing the magnetic field, this domain of spin right increases, and eventually it eats them all up. So in the end, when you slowly increasing the magnetic field, you will be able to flip all the spins to the same direction of the magnetic field, And at that point, then we say that the ferromagnetic material has saturated this spin because there are no domain walls at all. So this is the basic mechanism underlying the permanent magnet. So if for ions, initially the system may have clusters of spins that having the same direction, but in total, on average, this could still average out to have no total magnetization. But if you add some magnetic field slowly, and it will be able to convert all these random direction domains to be the exact same spin pointing exactly along this magnetic field direction. And we can plot the current used to magnetize the ferromagnetic material, and the function and so here we plot the magnetization vector m as a function of this current I. So the current produces the H field, right? So because we know that the del dot H is related to the I free. Sorry, the del cross H, right? So the I here produce a H field, and this H field, or you can think of this magnetic produce a magnetic field, and this magnetic field will magnetize the material and produce a finite M. And because M is finite, then the total magnetic field B is also finite. So and it will be enhanced hugely by this M vector. So now initially, say we have a magnet that's not polarized yet, so it's just a normal ion. And now, as we slowly ramp up the current, the magnetization vector increases until it saturates. So the saturation point is when all the spins have been converted to align with the magnetic field. Now, what's interesting is that once you reduce the current, it doesn't necessarily follows back this curve. So instead, what it does is that it actually lags behind. So what I mean is that even though you are reducing the current, the M vector is not changing as much as you have imagined. And even if you reduce the electric current to be exactly zero, there is still some residue left here. So that's the mechanism of magnetizing a permanent magnet. So you see that in this point, even though even though the magnetization vector here is not fully saturated, but there is still a fair bit amount of this M that's being left over, and that explains how you magnetize a magnet. So typically we apply some slowly applying a current, and then ramping down back the current down, and then what's left over is some permanent magnet. So in this process, now if you ramp the current continue to the backwards direction, so you will reach a point where the magnetization vector reaches exactly zero. but you need a current that's actually negative in order to reach that point. Now this loop can continue, and if you increase your negative current, you will magnetize your magnets in the other direction until it saturates. And now as you change the current, so you run the current backwards, right? Yes. So if you so at that point you reach another saturation point, where all the m points along the exact opposite direction of the point over here. And this process can, if you continue to go back and increase the current, what you get is then the inverse of this curve. So it will follow back to the point over here. So you see that it's a closed loop, but now it's never go back to the origin here. So it's easy to magnetize a permanent magnet, and once the magnet is permanently magnetized, it's actually not easy to get rid of that magnetization. What you can do is to maybe to weaken the magnetic force produced by the magnet by changing the orientation of this magnetization vector, but it never really disappears. Any question?
Can I use entropy to show the phenomenon where it cannot be? When once you are magnetized, then that will happen.
So if you want to go back, there are still ways to go back. Yes, the entropy is related. That so the entropy of the system at here is large, and the entropy that's where the magnet is magnetized, the entropy is typically small, and so but let me see. So, but there are ways to go back to this point. That is, if you heat the magnet up and until it transits to the paramagnetic regime, then you can demagnetize your magnet. But sometimes, so the size of this loop is actually relates to the energy dissipations so here you can sort of imagine that when you are magnetizing the magnet, you are actually doing work, and eventually once you close up this loop, when you are magnetizing the object, the work that you have done will be converted into heat. So imagine that when you are magnetizing the magnet, you are losing the entropy in the spin in the spin degree of freedom. So this kind of energy, so you are decreasing the energy of this in a spin degree of freedom. So this energy must be converted to somewhere, and that's the place where your energy goes to, is going to the heat. So that is every time you magnetize objects, you are actually producing some fair amount of heat. And so when you want to produce a permanent magnet, you might want a hysteresis loop that is large. But say that if you want an electric motor In these cases, you actually want a hysteresis loop that is extremely small to avoid the excessive heat when you are magnetizing your motor. And another point that I want to emphasize is that the B field produced by this magnetization is huge compared to this H field. So when you do this hysteresis loop, even though the bare H field is extremely small, once you put an ion core inside your wrapped coil, the magnetic field it produces can be 10 to the order of 4 times larger than what you have for the bare case without this ion core. So typically when you want to produce a strong magnetic field, we don't only have wrap a solenoid. We always have an ion core inside of that solenoid of wires. Okay, so next chapter we will discuss the electrodynamics, and I want you to try to go back to this chapter 9, I guess. Yeah, chapter 9 of this of the physics 2041. So we will discuss the electromotive course first, and so what we first will discuss is the Ohm's law, and so for the Ohm's law is the reason there is Ohm's law is because that there is a subtle relation between this current density and the electric field. So imagine that when you to push this charge and to make a current flow, you have to supply some kind of force, and then this force, the current is actually proportional to this force per unit charge. However, in this force is the Lorentz force. It should be written down as E plus V cross B, right? But typically the velocity of the charge is small, and according to the homeworks, the velocity field, the force produced by this magnetic field is negligible compared to the electric force. So that's why we get this Ohm's law as the current J equals to the conductivity times the electric field E. And then 1 over the conductivity is the resistivity that you are familiar in the physics 2041. So for this Ohm's law, we can so this Ohm's law is actually not something trivial, even though we have seen it multiple times, and it seems logical, but in fact it's a subtle law that even though it's as simple as it looks, the explanation of the Ohm law is not simple. So here the Ohm's law is to explain this Ohm's law, you have to use the Joule model. So I don't know if you still remember this name. So the idea is that now for a perfect conductor, there is no such thing as Ohm's law, right? Because for a perfect conductor, if you apply a voltage difference, then it doesn't make much sense, because a perfect conductor means equipotential surface. So there cannot be a surface charge difference. So here, if you apply a tiny little voltage difference, then the current will flow freely from one side to the other side. And however, here we are considering some non-ideal conductors. So there is a conductivity, and what it means is that when the particle or when the charge is accelerating from one side to the other side, there are some heating that's going on, and this heating will slow the charge down, and actually somehow magically it will slow the charge down to a constant velocity. So this is extremely tricky, because it's a force that's similar to a friction, and where the friction, the microscopic nature of this kind of force is not easy to understand, because down to the microscopic level for the explanation of the friction, you have to include the electromagnetic force between the atoms, and because of this collision of the atoms over the two surfaces of a material, there can be a friction. And likewise, here for this current in a non-ideal conductor, there are collisions between the free accelerating electron and some static ions in the conductors. So you can sort of imagine that in the conductors there are some fixed position ion cores, and the electron will accelerating to the right and then be bounced, and then accelerate again and be bounced. So it will spend a lot of times inside of this conductor, and finally the average change of the velocity is slightly towards the right direction, and this drifting velocity is the velocity that we are interested in. And because of this very slow drift of these charged electrons, there can be a current. So try to go back to chapter 9. You can see some discussion about the Druid model, and try to get an understanding of this Druid model from the Physics 2041. And in the next lecture, we will start the chapter 7, and we will begin discuss some Ohm's law, and also try to get a review of the electromotive force. So in the chapter 9, we discuss the electromotive force. It's not finished yet. So the electromotive force, you have to make sure that you know the definition, that it's called the EMF and it's measured in volts, but it's not a force actually. And try to get a review of that also in chapter 9. Okay, that's all.